Hello everyone. Today we have a topic on numerical solution of differential equations. This is lecture 1 and followed by lecture 2, and if possibly it will be 3. So differential equation is a very important part of applied mathematics, and a differential equation is a relation between a function, its derivatives, and the variable upon which they depend. And you have learned about so many techniques in differential equation. You have applied those techniques. You know how to solve second order linear differential equation. You know how to solve higher order differential equations also with several methods. So today we are talking about numerical solution of differential equations. That is our topic. How to solve differential equations numerically. So before we go to the main core of our topic, let's come to the basic concepts. So here we shall be concerned with the numerical solution of a differential equation of the first order. It's given by 1.1 dy dx equal to fxy. Subject to a given initial condition ya equal to y naught. That means at x equal to a, the value of y is y naught. That is the initial condition. The computed solution will be obtained in the form of a table for a number of values of x lying in a selected neighborhood of a. So that is the problem. Now, more precisely, we choose an interval a comma b and a partition of a comma b. So let us divide the interval a comma b in a small subintervals. That means the partition of a and b. And the point of partitions are taken as a set omega x0, x1, xn. That is a set of points for which a equal to x0 less than x1, etc. less than x1 equal to b. That's the partition. That's the partition. Okay. Such that the values of the solution yx at the points, these partition points x0, x1, xn, are to be computed. The set omega, that is, it contains the partition points, the set of points is usually called the grid or mesh, and the points xi, the grid or mesh points. So this set is actually the grid or mesh set of points, and the points xi I equal to 0, 1, 2, etc. up to n is called the mesh points. Usually, the grid points are taken to be equally spaced. Point to be noted, everyone, that the points are equally spaced rather than unequally spaced. That is xi equal to a plus ih, h equal to b minus a by n. Okay? Just like in the integration process, we're doing this type of special advantage of taking this partition, where h, called the step length, is usually chosen. You have to choose that. Okay, everyone? Now, the exact solution will be denoted by yx, and we shall write yi equal to yxi. And the computed value of yi will be denoted by yi bar, I equal to 0, 1 to n. Also, we shall write fi equal to fxi x. This is the notations. Fi you can write f at xi yi. Fxi, that is the partial derivative with respect to x at xi yi. Again, you can take second partial derivative, double partial derivative, fxxi at xi yi. These are the points. So, etc. These are the notations. Now, what is the error in computation? The error epsilon I in the computed value yi bar of yi. Actually, you see yi is the exact value and the computed value is denoted by yi bar. So you have yi the exact and yi bar the computed value. Okay. Now epsilon I is given by yi minus yi bar. That is the exact value minus the computed value by the given initial condition, this 1.5. So that epsilon 0 is 0. Initial error was 0. So the error on the grid or the grid error to be denoted by E omega, or you can denote it by simple E also, that is to be denoted by, defined by maximum over 0 to n mod epsilon I. This E is actually the grid error, and it is the maximum over mod epsilon I, and in the interval 0 to n, which is a function. Clearly the grid error is a function of the step length h, apart from depending on the given function fx and the initial value y0. It also depends on the step length h. Okay everyone, so this grid error is given by 1.6, and these are all points actually. This is the typographical error in my laptop. Okay, next come to another important concept, that is we shall be talking about single step and multi-step methods. The methods for the solution of the initial value problem, that is we are talking about this type of problem. Yes, initially we denote it by ya at y0. That's fine. Now we are denoting yx0 equal to y0. That means at x equal to x0, the value of y is y0. That is the initial condition. Okay, that was the your equation 1.1. That is, I am talking about the previous equation. Can be classified mainly into two types. You can classify this type of initial value problem into two types: the single step method and the multi-step methods. That is, the methods for solution of the initial value problem can be classified into two types: single step methods and multi-steps method. Now the question is, what is single step method? In single step methods, the value of yi plus 1 bar, that is the computed value at I plus 1, depends on the knowledge of the preceding value yi bar. That is, if you are calculating the next computed value of y, then it depends on the previous value, just preceding value of yi. That is called the single step method. But in multi-step methods, look at that, the value of yi plus 1 bar depends on more than one of the preceding values, yi bar, yi minus 1 bar, etc., yi minus 2 bar, etc., all the preceding values. It depends on all the preceding values. But in single step method, yi plus 1 bar, it depends on only the preceding value, yi bar. That is the difference between single step method and the multi-step methods. A method in which yi plus 1 bar depends on k preceding values, it is called k-step method. If it depends on 2 preceding values, 2-step method. If it depends on 3 preceding values, 3-step method. Similarly, it's a k-step method. So that is about single step and multi-step methods. Okay, everybody? Now, next. Thus, in a single step method, the initial value changes with every step. The initial value for the I plus 1th step being yi bar. In a k-step method, the computation cannot be started until and unless the values of y1 bar, y2 bar, etc. are obtained by some other method known as a method for starting the solution. So that is the disadvantage of the k-step method, multi-step method. Okay, but in a single step method, the initial value changes with every step. You will get the initial value of the I plus 1th step and being used in yi. Next, I shall be talking about explicit and implicit method. What is explicit and implicit method? It's a very simple thing, because if the value of yi plus 1 depends only on the values of yi, h and fx, f at functional value at xi, yy, then the method used to determine yi plus 1 is called explicit method. Otherwise, it is implicit. So if the value of yi plus 1 depends only on the values of yi, h, and if a functional value at xi, yy, then the method is used to determine yi plus 1. It's called the explicit method. Otherwise, the method is called implicit. That's the explicit and implicit method. Now, let's come to the single step methods. We will talk about error and convergence. So let's write the general form of a single step method. A single step method consists in determination of a function which is a function of x, y, and the step length h, and depends on fx, y and its derivative, such that y at x plus h, it's given by yx plus h function of x, y, h, and plus etc. order of h to the power p plus 1. That is why Taylor series. So this is 1.7. So this is the general form of the single step method, where p is an integer, positive integer is called the order of the method. So if you expand, you will get this type of form, 1.7. Now putting x equal to xi, you will get yi plus 1, and this is denoted by yi. That means at x equal to xi, yi means it denotes the value at x equal to xi. Yi plus 1 means it denotes the value at xi plus h, plus h phi of function of xi, yi, and h, and order of h to the power p plus 1. That makes 1.8, equation 1.8, where modulus of order of h to the power p plus 1 must be less than equal to some constant a and h to the power p plus 1. This is 1.9. Okay, this is 1.9. Now, then neglecting the last term, I'm neglecting the last term because it's an order of h p plus 1, and replacing yi by y plus 1 by their computed values yi bar, yi plus 1 bar, respectively in 1.7. You look at that 1.7, if you replace these values by bar, we get the recursion formula. You got a recursive relation, and you are getting this formula together with the given initial conditions at y naught bar equal to y naught, and this is the recursion formula 1.9. What is it? Y plus 1 bar. This is the computed value, and previously it was the exact values. Okay, yi plus 1 bar equal to yi plus h function of xi bar plus comma yi bar h I equal to 0, 1, 2, 8, etc. And you are neglecting the last term, by which this recursion formula, from this recursion formula, you can determine the values of y1 bar, y2 bar, etc. y1 bar are successively determined. Okay, the term you have neglected in the previously, you have neglected the last term, order of h to the power p plus 1. This is called the truncation error or error in the method. Okay, in the above approximation, if you neglecting this, is called the truncation error. You got an idea of the truncation error. Now let us estimate that error. Let us estimate that error by virtue of our assumption that fx, y and its partial derivatives of sufficiently high orders are continuous in the closed rectangle. If you take a closed rectangle, it follows that phi of x comma y comma h and its first order partial derivatives are continuous, hence bounded in D. That is actually follows from Lipschitz condition. Let then partial derivative with respect to y, phi y x y h less than modulus less than equal to b. B is a constant in D, this closed rectangle, so that for y comma y bar belongs to CD, and phi of xy h minus phi of xy bar h equal to, if you take the difference of the exact and the computed, y minus y bar phi y xy star h. That is a useful relation. You know this relation, where y star lies between y and y bar, and hence if you take the modulus both sides, this less than equal to b, so this must be less than equal to b mod of y minus y bar, because phi, you see, it's from 1.10, it follows from 1.10, and this is your 1.11, where y bar belongs to CD. So you got relation 1.11 less than equal to some constant into the modulus of the difference of y and y bar. Next, we will use the notations I plus 1 I. If you write this from this and these relations, this both the relations we have mentioned earlier. So from this we'll get, if we substitute here, we will have, if you take the difference of these two equations, from these two equations, this can be written as yi plus 1 modulus of yi plus 1 bar less than equal to yi minus yi bar plus h function of xi yi h, and this function of xi yi bar h plus modulus of order of h plus 1, and this must be less than equal to some constant to h to the power p plus 1 that is earlier mentioned. So we can write this equation, which keeps the recursive inequality in error form, because this will give you the error, this modulus will give you the error at every step. So that is given by mod epsilon I plus 1, error at the I plus 1th stage less than equal to 1 plus hb epsilon I, and this a h to the power p plus 1. This is easily calculated from the error relations. This is 1.2, okay, 1.12. So you have a recursive inequality in error. Now writing temporarily, 1 plus hb is a constant, it is, let it be lambda, and mu equal to this. So your modulus of epsilon I plus 1 less than equal to lambda mod epsilon r. If I write this in terms of lambda and mu, then this is written as this. Hence, again writing, what I'm doing, I'm successively substituting values. So I'm writing epsilon I plus 1 less than equal to lambda. Again, I'm writing lambda epsilon plus I plus mu lambda square epsilon I plus I minus 1 plus mu 1 plus lambda. So successively I'm getting a relation. I'm writing I minus 1, I minus 2, I minus 3, etc. You will get this type of relations. Finally, you are getting this. Noting that epsilon naught and replacing I by I minus 1, we get modulus of epsilon I less than equal to mu lambda I minus 1 by lambda minus I. 1, I equal to 1 to n. That's the error relation. Because it's a GP, geometric progression, you are getting this relation. Okay. Since, as we know, ipsi e to the power x greater equal to 1 plus x, so we are getting this 1.313 and 1.14. This shows that for a single step method of order p, the grid error is given by order of h to the power p. This is the grid error in a single step method. Okay, this is the calculation for a grid error at every step. This is the simple calculations by using e to the power x greater equal to 1 plus x. Now, what about the convergence? It follows from 1.14. You look at that 1.14. This is the equation 1.14. That e tends to 0 as h tends to 0 or n goes to infinity, and such that single step method invariably converges. That is very, very important. Invariably converges. Okay, everyone? Now let's talk about Taylor series method. What is Taylor series method? Let us consider the first order differential equation, dy dx equal to fxy. This is the equation, and if you exact solution at x equal to x naught, if you apply Taylor series, you will have y naught, y1 dashed, y1 double dash, etc. derivatives, and because the power series of x, the derivatives can be obtained by taking a total derivative of fxy, right? So this is the method of Taylor series. You can calculate these values at every step. So this is the general Taylor series method expansion for order n, 1.17. And what about the error? The final global error of Taylor series method is of the order of h to the power n plus 1. Thus, for large value of n, the error becomes small. If n is fixed, then the step size h is chosen in such a way that the global error becomes as small as desired. Okay, everybody? So that's the Taylor series method and its error calculation. And that's, I will stop here. Everyone, thank you. Follow my lectures.